Okay, can everyone hear me? People in the back, can you hear me? Is the mic working? Okay, good. Oh wow, fewer people this time. Great, great. So I guess there are a few questions people asking about people who are waitlisted in the class. I don't think that should be a problem because a lot of people will drop out. That's kind of what happened last year. So people who are on the wait list will eventually get in. Okay, so I don't worry about it too much. There were also a few questions about online. So these lectures are going to be recorded, so you can watch them online. I think that they're working with a few issues getting the lectures online, so it's going to take a couple of days. If you have your Andrews ID, you should be able to log in into Canvas or Blackboard and be able to kind of watch the lectures online as well. So, you know, for those of you who want to do it remotely, you can do it remotely. Any sort of, before we start the class, any other logistical issues? Oh, one other thing is that the prerequisite for this course is 10601, which is the Intro to Machine Learning. And if you haven't taken this class, it's really going to be a tough class to take, this one. Right, so I would prefer for people to take 10601 before you can take this class. The other thing that I typically advise most of the students is that look at the pace of the class and, you know, make a decision for yourself whether you want to take this class or not. Don't be in a situation where, you know, sometimes in November you come to me and you say, I have no idea what's going on in the class. How do I not fail? Right, so it happened to me before. So I'm okay if you're taking the class, if you have the background, but just look at the pace of the class and ultimately make a decision for yourself whether it's you're going to handle it. Okay? Any questions? Yes, Piazza is going to be set up today, tomorrow. I'm also going to introduce TAs. We have 4 TAs. It's probably going to get a couple of more. Next week, I guess we don't have classes on Monday. Is that right? Monday is a holiday, right? Okay, so we're not going to have class on Monday, but by next Wednesday, we'll set up Piazza. We're also going to be using Gradescope for submitting your assignments. So I'll announce it later on how to register for Gradescope, for Piazza and such. And we're also going to have office hours that TAs are going to be holding every week. Okay? Any other logistical questions? Okay, so we have a lot to cover today. We probably won't be able to cover everything, but let's actually remember where we stopped last time. We started looking at statistical decision theory, and again, I just wanted to give you a very brief introduction into statistical decision theory so that some of the key concepts that we're going to be covering for the rest of the class you'll be aware of. So again, the key idea is that if we knew what the joint probability distribution of the inputs and outputs is, that basically provides the whole summary of all the uncertainties that we're trying to measure. And determining this distribution from data, from training data that you observe is known as the inference problem, right? And remember last time we've looked at this simple example, right? So let me just remind you what it is. We're trying to solve a classification problem, right? So given an input, which is a set of pixel intensities, we're trying to figure out which class the input belongs to. But at the end of the day, we have to make a decision, right? So ultimately, your predictions are going to be fed into some kind of a decision-making mechanism. And remember, last time we've looked at this Bayes rule, or just looking at the conditional probabilities, where we say, well, the conditional probability of a particular class is going to be given by the likelihood function. This is sometimes known as the likelihood function, which is the probability of all the data or all the pixel intensities in your data given a particular class, the prior, and then the normalizing constant, right? And remember last time we briefly mentioned that if our goal is to minimize probabilities of assigning X to the wrong class, then you should choose the class with the highest posterior probability. right? And that's exactly what's happening in most of the deep learning applications, where I give you an image, I want to classify whether you see a cat or a dog in the image. You compute the posterior probability of an image belonging to the cat class versus a dog class. You pick the maximum, and that's your decision. Okay. Now, there's something that's known as a loss function, which is the overall measure of loss that you're incurring by taking any available decisions. Right. So, for example, suppose that for x, the true class is C sub k, but we assign x to class j, right? So we make a mistake of assigning x to a different class. We're going to be incurring the loss LKJ, which you can think of as kjth element of a loss matrix, right? So it tells you something about what's the loss that you would incur if you make the wrong prediction. Okay? So let's look at, again, the medical diagnosis example. And let's say we have the following loss matrix. If the truth is that the person has cancer, and your decision, your model basically predicts a cancer, then the loss is 0 because you made the right prediction. If the truth is normal and your decision is normal, then the loss is 0, right? You're not incurring any loss because you've made the right decision. If your truth is normal, but your prediction is cancer, well, that's not good, right? Because you're effectively, freaking out the patient. So there is like, there is some loss you're incurring. But if you look at this problem, that the truth is the person has a disease, and your model says, no, you're okay. That's basically your loss is really high, right? Because it can lead to big consequences. Yes, question?
Why do you have the numbers 0 and 0 in the diagonal part?
So the reason why we have 0, 0 in diagonal parts is because we're making correct predictions, right?
But that's the loss.
That's the loss, yeah.
So in off-diagonal parts, why do you have different losses?
So in off-diagonal parts, the reason why we have different losses is because one mistake can cost you much more than another mistake, right? So that's exactly what I'm saying here, is that if the truth is that the person has a disease and your prediction is that no, you're okay, then it carries a lot of loss because the patient can die, right? Whereas in another case, if your prediction is normal, but if your prediction is that the person has a disease, but the person is actually normal, yes, it's annoying because you'll probably start going through additional tests. So you're incurring some loss, but it's not as loss compared to the other type loss. Yeah.
Sorry, I have one more question.
Sure.
Regarding the absolute values of these numbers, is there a higher?
So yeah, good question. So how do we choose these numbers? These numbers are typically chosen by the modeler. So whenever you design a system and when you design your own model, a loss function is something, a loss matrix is something you have to design as a modeler, right? Based on your prior knowledge or how you, what the problem you're trying to say. So if you think about the expected loss, well, it's just basically, it's set up as this formulation, which is essentially looking at decision regions or decision boundaries that you're trying to choose such that you minimize the expected loss, right? So you're basically summing over all entries in your matrix. Let me look at the following example. Let's say that we have x, which is a real valued, again, output. We try to model a real valued target for a particular x. And the decision step consists of finding an estimate for each input x, right? For every single input x, I have to make a prediction, y of x. So now we want to figure out, what does it mean to do well or to do badly on this particular task, right? So we have to define some kind of a loss function, right? Because I can give you a prediction, all right, for a particular input x. Now, if I specify the loss function, right? Again, that's up to me. That's a modeler's choice, which basically says, how good my fit is, right? This is my prediction. This is the ground truth. The average or expected loss is given by this expression, right? That's ultimately what we want to optimize. But do you see a problem with optimizing this expected loss? The problem is that we never have access to this quantity, right? It's like, if I knew perfectly what's the uncertainties associated with my model or with the ground truth, then I could, optimize for expected loss. So for example, but we never have access to this, and we'll see how that affects us. In fact, most of the time, we're going to be building model of your data. We're going to be building either generative models, which effectively trying to model probability of x and t, or we're going to be fitting conditional models, which is effectively trying to model conditional probability of t given x. But this is, if we're looking at a squared loss, which is the commonly used loss, then you can say, well, for this particular regression task, we're going to be looking at that as a measure of our goodness, how good we are performing. Okay? So this is known as a squared loss. This is probably the most commonly used loss. And it turns out that there is an optimal solution, right? And the optimal solution, if we assume a completely flexible set of functions y of x, and we don't restrict y of x in any way, we think of the most complex function y of x, then it's going to be given by the conditional average. So it turns out that if I want to solve this problem, then my optimal function will have this form, right? Which is the conditional expectation. And so the idea here is that if you have a regression function that minimizes this expected squared loss, then it's given by the mean of the conditional distribution. Okay? So what does that mean? That means if your loss function is a squared loss, then all I need to do to solve this problem is to really figure out what that quantity is. Right? The conditional probability of the targets given the inputs. And in fact, if you look at a lot of deep learning models, convolutional networks, neural networks, something that we're going to be probably a third of the class will dedicate to that, a lot of these models are effectively trying to model this conditional probability, right? The conditional probability of the targets given the inputs, particularly for regression problems. So we'll see that. Now, let's figure out why this is the optimal solution, okay? And let me just walk you through a little bit of a proof to see that this is an optimal solution. Let's say that this is what I'm trying to optimize. I say subtract the expected value of the targets, add the expected value. So I haven't really done anything here. Now if I open the parentheses here, I'm going to have this expression, right? Which is just opening the sum of the squares, right? So you can see this is squared, it's over here, 2 times the cross product between these two. Now, if I plug it into the expected loss, right? If I actually look at the expectation of this quantity with respect to the joint x and t, with a little bit of manipulation, a little bit of algebra, I'm going to end up with these two terms. Okay? So let's look at what these terms are. What is the first term? The first term is basically saying take this quantity and look at its expected value. This term is the variance. And what is the variance? That's the variance, right? Because note that it's expected value minus the target itself squared. That's the definition of the variance. Okay? What happens here? It's 0. That's right. The reason why it's 0, because if I take expected value, this term will become 0. Right? Because this expectation, and if I take an expectation with respect to t, this term will become 0. So now we have something interesting, right? If you look at this quantity here, the expected loss is minimized when I have my function, my predictor that I'm trying to build equals exactly the conditional expectation, because then this term is going to be 0. Okay? And this term here is the intrinsic variability of the target values. Right? So think of it as the noise. This is the noise in the targets. Sometimes it's known as a measurement noise. You can't really do anything about it. It's, if you're trying to conduct measurements, it really is telling you how much noise you have in your measurements. Right? So this is kind of like the lowest achievable expected loss that you can ever get, right? Think of this, the thing that, like sometimes you watch Hollywood movies and they take a picture and then the boss comes in and says, hey, zoom in on this part. And you like magically zoom in and you start seeing license plates of vehicles and stuff like that, right? Well, this quantity is telling you can't do that. You can't go beyond the resolution of the image that you've taken, right? So there's going to be intrinsic noise, how much you can get from the data. And it's independent, and it's independent noise. It represents the reducible minimum value of the expected loss, right? So that thing you can't control. The variability of your labels you can't control. Well, for many of you, how many of you are familiar with the ImageNet data set? Okay, so many of you. So ImageNet is kind of like a big data set for classification. And if you look at this data set, a certain fraction of images are actually mislabeled, right? You look at the image, somebody says there's an elephant. You look at the image and then there's a car, right? So that basically, tells you that there is some noise in the targets. You can never go beyond that noise, right? You can never have zero test error because it's impossible. So now, in terms of this particular loss function, that's, it's a proof. You can use other ways to prove that it's that the optimal point here is the conditional expectation. We sort of cheated a little bit because we plugged in the right answer, opened up the parentheses, and kind of like showed that that's what it is. You can use calculus of variations to actually do the proof, and maybe on your first homework you'll play around with these models. You can also use other generalization of the squared loss called Minkowski's loss. If you squaring it, the minimum value of the loss is given by the conditional mean. If it's 1, it's an absolute value, then it's conditional median, right? So you're looking at the conditional median of probability of t given x. And if you set q and you let it go to 0, you're going to have a conditional mode, right? So you will find, the most probable configuration. So depending on what loss functions you choose, you'll have different solutions. And for different problems, certain solutions might make more sense than other solutions. Okay, now, there are two types of approaches that we'll talk in this class. There's one particular approach known as a generative approach. And this is something that we'll focus on in the second half of the class, specifically, looking at the deep generative models. The generative approach models the joint density, right? The probability of x and t. In particular, most of the time you're going to be modeling what's the conditional probability of x given t. Think of x as an image and t is the class, right? So here you try to really build a generative model of a cat or a generative model of human face, right? And that's the probability of t. Or you're trying to model it for classes or for regression models and such. So you're always trying to model some conditional probability. And then you're going to be inferring the class conditional density by using Bayes' rule. Right? You're going to say, in order to predict what this target is, I'm going to be using my likelihood function times the prior and then renormalizing it. Okay? So this is known as a generative approach. The reason why it's called generative is because you're trying to model this quantity. Right? So some people are working on generative models of images. People are working on generative models of music, generative model of language. Right? Can I generate a sentence? Right? Can I generate a sentence that's pessimistic? Can I generate a sentence that's optimistic? It's useful for sentiment analysis. And then another approach is discriminative, right? So in discriminative approach, you model the conditional density directly. So if you look at most of the neural networks, convolutional neural networks, lots of success stories are really trying to model this conditional probability directly, right? And we're going to cover both of these approaches. Now, just quickly, what are some advantages and disadvantages? Modeling discriminative approaches have been mostly successful so far. For image recognition, speech recognition, this is what we're doing. It requires one thing. So these conditional probabilities require us to have lots and lots of labeled examples. because we really have to have pairs X and T. So from X, I go to T, to my target. So think of T as your labels, X as your input, right? So you need to have both. In generative approaches, you can also incorporate, sometimes you can also incorporate unlabeled data. So if you have some knowledge of P of X, you can incorporate that into generative models. And we'll see some examples of that. The disadvantages of generative approach is that it's very hard to build these probabilistic models. Like, how do you build a very good generative model of a cat, right? Or how do you build a very good generative model of a human face, right? Or generative model of a music, or a sentence, so you can do sentiment analysis, right? So this is a very active area of research in particular in machine learning and deep learning, how to use unlabeled data to do that. These approaches have been a little bit more successful, but they also come with caveats. Just to point you the examples between the two, I think back in the early 90s was a very interesting example highlighting some of the deficiencies of discriminative approaches. Late in the 90s, I don't remember where, but people use neural nets to basically predict whether there is a tank in the image or not a tank, okay? You can see applications that could be useful there, but I show you the image, and if there is a tank, you want your model to say there is a tank. If there is no tank, okay? So they collected the data, trained this model, this neural net model, and it gave perfect prediction, 100%. You showed an image of a tank, it says this is a tank, on the test data. And people were very like, wow, this works really well, no mistakes. And then they figured out that what's actually was happening is that they took images with tanks on sort of cloudy day, and images without tanks were on a sunny day. So what the model was doing, the model would just basically look at the top pixels, look at the average of the top pixels and say, if it's gray, say there is a tank. If there is sun, like latter set of pixels, say there is no tank. It worked perfectly, right? So this is what these discriminative approaches are doing. These discriminative approaches are basically trying to find out features in the data so that you can classify it correctly, right? And that was the right feature, because for this data set, perfect generalization, right? The generative models are slightly different because the generative models are basically trying to say, what's the distribution of the pixel intensities given there is a tank or no tank, right? So now you actually have to build a generative model of a tank. And you have to build a generative model of skies and landscapes so you understand what's going on in the images, right? Which you can see is much more difficult to do, but this particular approach, the generative approach, would you know, probably fail less in that particular scenario, right? Okay. One of the things that I would like to point out also is that, and we'll see later in the course, is a linear basis function approach, right? So remember that the simplest linear model for regression is something that we've covered in the last class. It's just a linear combination of your features, right? And remember, the key property for these models is that it's a linear function of parameters, right? However, this is also a linear function of the input variables. Instead, what you can do is you can consider this particular model, where these phi's are some fixed set of basis functions. So phi's could be nonlinear transformations of the input, right? In fact, if you're familiar with kernel-based methods, this is the basic idea behind kernel-based methods, right? Transforming your inputs using some nonlinear function into nonlinear feature space and then applying a linear model in the feature space, right? So phi 0 is typically set to 1. You have a bias, but you can have that particular model. In simplest case, you can use linear basis functions by just picking linear subsets of your input, right? And so if you have these nonlinear basis functions, you can basically you can be nonlinear function of the input space, right? And so if you look at the, there's a lot of work even today on figuring out what these basis functions should be, right? Kernel-based methods, support vector machines, Gaussian processes, a lot of state-of-the-art techniques are using these ideas. When we start looking at the deep neural nets, we can also think of deep neural nets as doing something of this form, but where you're actually trying to learn what these basis functions are. And there's some interesting work of combining deep learning with kernel-based methods where you're trying to learn what the right kernels are. But let me show you some examples of the basis functions. So this is an example of polynomial basis functions, right? So you take your input and you just raise it to the jth power. So basis functions here are global because small changes in x affect all basis functions. Here's another example of a Gaussian basis function, a very commonly used one. So some of the hyperparameters is the mean and the variance, or the scale. Sometimes this is called scale. This is the mean. In this case, basis functions are local, so small changes in x affect only nearby basis functions, right? So like if I change x here, this basis function is not going to be affected because it's still going to be 1, right? And this is probably the most commonly used basis function expansion, Gaussian basis functions. Or sometimes they call exponentials. You can also use sigmoidal basis functions, and again, these basis functions are local. Small changes in x only affect nearby basis functions. And again, the mean and the scale are controlling basically the location and the scale of these functions. Again, these hyperparameters, these sometimes called hyperparameters, have to be specified by the modeler, right? Or via some kind of cross-validation procedure. But that's a way of kind of encoding your data using these basis functions. The trick is that the decision boundaries will be linear in the feature space, in the projected space, but would correspond to nonlinear boundaries in the original space. Let me give you an example, right, of that particular thing. So classes that are linearly separable in the feature space might not be linearly separable in the original space, right? So it's a whole idea of you take some data, you just transform it into the feature space so that you can build a linear classifier, right? That's basically the idea behind a lot of ML algorithms. Let me give you an example. Suppose I give you this particular space, and these are these are points belonging to class 1, and these are points belonging to class 2, right? Obviously, it's a nonlinear function in this space. But if I use basis functions, Gaussian basis functions, this is the first Gaussian basis function, this is the second Gaussian basis function. So I'm just doing nonlinear transformation with respect to exponentiating and looking at the distances to the mean of each one of the basis functions. Then once I do the projection, I'm going to get this particular representation in the feature space, right? And if I build a linear function here, this linear function in the feature space will correspond to this particular decision boundary in the original space, right? So when you think about linear models, don't think of fitting lines, right? Because if everybody tells you, yeah, I'm going to be building a linear model, it really is a linear in the parameters, but the representation of the input could be nonlinear, right? So that's why, and again, how do you find these basis functions? What are the right parameters for these basis functions? That's something that you have to either cross-validate or you have to do some kind of fitting by yourself, okay? Right. And the way, I guess in this particular case, because it's a classification problem, the way you obtain this decision boundary is just fitting logistic regression to this data, right? Which is a fairly simple thing to do and has an optimal solution. In terms of the maximum likelihood function, as before, throughout the rest of the class, mostly we're going to be working with probabilistic approaches. So in this particular case, again, we're going to be making assumptions that the data that we see, the observations that we see, they come from deterministic function with an additive Gaussian noise. So we're going to be modeling this conditional probability as a Gaussian with mean given by our prediction, right? Could be nonlinear function or a linear function and some variance, right? So now if I give you a set of inputs and the corresponding target values, under IID assumption, I can write this joint probability distribution as a product of individual terms, right? Because I'm going to be making assumption that every single x is independent of another x. So x2 is independent of x1, and all of them are independent, which basically means that I can always write it down as a product of all the data points. And my prediction here is exactly the same as what we're seeing in a linear model. I have some nonlinear transformation of my x. I take a linear combination, and that's my prediction, right? So nothing has really changed from going from simple model to this a little bit more complex one. So F here is just a big matrix from 0 all the way up to the m, where m is the number of basis functions you're using, right? And this is something that you also should keep in mind, is that if the dimensionality of your data is d, and you're using the number of basis functions m, then the complexities of whether you work in the original space or in the future space depends on what your m is, right? How many basis functions you want to use. So taking the logarithm, you have this expression. Again, just a little bit of algebra. You look at the Gaussian expression. If you look at this particular thing, again, it's just the least squares, right? Nothing has changed from the first class. This is just the sum of the squared error. If you differentiate, you set to 0, right? You get this expression. Just a little bit of algebra. This is the derivative of the log likelihood with respect to parameters w here. Solving for w, you get this expression, right? So phi here is known as a design matrix. Again, this is just the least squares, but the least squares in a feature space, right? And so phi here is known as a design matrix. It's n by m matrix. N is the number of examples. M is the number of basis functions that you're using. And again, the number of basis functions here is being specified by the modeler. So it's up to you to design what that thing should be. Yes? Yeah, absolutely. Later on, we'll go into the overfitting. But yes, indeed. Generally speaking, that choice is, how much expansion. Like if you're working with three-dimensional data points and you expand it into 1,000 basis functions, just styling up the space, then yes, you may run into overfitting. So it's something that you have to control as a modeler. Yes.
So referring to that question, so when you choose a basis function like for difference of Gaussian and linear basis function polynomials, so with those basis functions, if you choose something where small change in parameter in the basis function can lead to huge differences in with phi 0 and phi 1 and phi 2 there, does that lead to overfitting?
Yeah, potentially it can. So the question is, what basis functions you choose. If you choose basis functions like, for example, polynomial, then yes, small changes in x will affect your basis functions a lot. So it really is a choice that you have to play with these basis functions and figure out for your data which one makes sense. Generally, if you look at the Gaussian basis functions or sigmoid basis functions, these are commonly used one. Probably Gaussian or exponential is the most commonly used one. But again, it depends on the problem. Those are all kind of design choices that you have to make. And this particular inverse is known as pseudo-inverse that I wanted to include. The other thing that I want to point out, and we'll come back. Yes, question.
Yeah, sorry, back to these real quick. I guess it wouldn't really be a linear model anymore, but you would practice one of the parameters of this basis function?
Yes. So if you fix the basis functions, then it becomes a linear model. Right? Because you can just use least squares. Think of it as like you have some data, you do some fixed transformation of your data, and then just fit a linear model to that. And if you look at industry, 90% of work is done using that approach. Take your data, find features from your data using basis functions and so forth, and apply a linear model. Now the question you're asking is that can you actually learn parameters of these basis functions? Yes, you can. We'll look at some of the approaches later in the class. But there are ways of figuring out what these parameters are. Then it's no longer a linear model, right? Because you're effectively changing this matrix. So then you can set up, gradient-based optimizers and such to figure out what the thing should be. There's a whole class of, there's a whole literature on something that's called kernel learning, where people also try to figure out, what if I find, a linear combination of kernels? Can I find the right linear combination of kernel functions? There's some very good papers and theory in that space if you're interested. Yeah. Okay, so one other thing that I want to point out very quickly, many of you are probably familiar with that concept, is the notion of sequential learning. I just keep on time. And the idea here is that the training data are going to be presented at one example at a time, and the model parameters are going to be updated after every single time you see a particular example, right? So you're basically saying the parameters at t plus 1 equals parameters at t minus some learning rate eta, and the gradient of your error function, of your objective function, of the squared error function with respect to the weights for that particular training example, right? And this is the learning rate, and this is the weights after seeing training example case t plus 1. So in case of sum of squared error function, you basically get this one, okay? And this basically is an instance of stochastic gradient descent. How many of you have heard about SGD? Okay, so many of you have, right? This is probably the most commonly used technique, and we're going to be using that technique a lot in this class. And for your homeworks, when you're going to be training these models, most of the time you're going to be using some version of SGD. So the training examples are picked at random, and it's a dominant technique when learning for very large data sets, right? The question for you is, why is this thing working at all? Like, we get one example, or maybe a few examples. You compute the gradients. Like, that's not the right gradient. Why does it still work? Any guesses? So the question is, here, if I take a single example and I compute the gradient and then start updating my parameters, you know, the gradient that I'm computing is not the right gradient, all right? Because the actual gradient for my loss should be the gradient averaged over the entire data set, right? That's my true gradient. What if I get the gradient that points me in the wrong direction? Because I happen to see like a weird example. Why is this technique still working? Sure, okay. Any other guesses? Yes. That's exactly right. So the idea here is that because I'm choosing these examples at random, on average, if you take an expectation, in expectation, it's the right gradient, right? So if you think about it, on average, I'm going to be moving in the right direction, right? So it's noisy, right? Because it's not quite the exact gradient, so there is noise. But on average, you're moving in the right direction, right? It's kind of like if you try to get to downtown from here, you kind of like, no, I should be going like this way. Maybe you'll stumble and go that way or that way, but on average, you're kind of like going to be moving in the right direction, right? And so that's why, you know, there's a very good theory behind SGD, but in general, on average, in expectation, you're moving in the right direction. Okay, so, and then you have to be careful about how you're choosing the learning rate so that you can hit the convergence. There's a little bit of theory behind that. Now, the other thing that I'd like to cover is this notion of regularization. And again, for the case of simple models, I'd like to cover it in a simple case, and we'll see most of these techniques when we're going to start looking at the deep nets as well. So let's consider the following error function. So we have a data term that we're trying to optimize and regularization term, right? So lambda here is called the regularization coefficient. Remember, we looked at this last class a little bit. So if we actually going to be looking at the sum of the squared error function plus this quadratic term, which is the L, sometimes known as the L2 penalty term, then we have this particular objective, right? So this is, again, this is kind of a regularizer. Remember last class we've looked at this particular technique. This is effectively forcing your parameters to stay close to 0. It's a one form of regularization, right? Because if your parameters are 0, basically that means your model is simple, right? So it's, you know, it's a way of making sure that your parameters don't grow to be too large, because large parameters typically in these models would mean that your function is very wiggly. Now, if you optimize this function, then you're going to get this expression. right? So if you if you look at the derivative of this function with respect to w, set it to 0, you're going to get this solution. And this is something is known as a ridge regression, right? And what it's effectively doing is you're adding a positive constant on the diagonal of your phi transpose phi matrix, right? So this makes the problem non-singular, even if this matrix itself is singular, right? In fact, this is how pseudo-inverse type of operations work. In fact, every time you try to inverse do the inverse of a big matrix, most of the time you just add epsilon to the diagonal for stability, right? And that's exactly what ridge regression is doing. And this is particularly important when the number of training examples is less than the number of basis functions. Because if that's the case, then your matrix is going to be singular, right? So you have to be able to regularize it. In fact, if you're doing regression for whatever task, you're almost better off using ridge regression. Pretty much works universally better than just doing standard regression most of the time. So if you think about the effect of the regularization, then if this is the function that you're trying to optimize, this is your regularizer, right? The regularizer says stay at the 0, and then you're trying to combine both of them. So the combined minimum is going to be on a line between the minimum of the squared error and the origin, right? So your minimum is going to be lying on on this line, and where exactly it lies will depend on your regularization coefficient, how much penalty you're assigning to your problem, right? And so this regularizer in particular shrinks the model parameters to 0. But there's a whole class of different regularizers, right, that have this particular form. You're solving some kind of squared error loss, or whatever your loss function is, but then you're taking it to the qth power, right? So if q is 0.5, you're going to have this regularizer. If q is 1, you get lasso, right? If q is 2, you get quadratic, and so forth. Back in '96, Rob Tibshirani introduced the lasso model, right? So, which basically, I'll show you later what the lasso does. Let me show you what the lasso does. Lasso is effectively penalizing the sum of the absolute values of the weights or of your parameters. And for sufficiently large lambda, for the coefficient, some of the coefficients will be driven to exactly 0. So you end up with a sparse model, right? In this particular configuration. And it turns out there is an optimal solution. It's a convex function. There's an optimal solution to solve it, right? And lasso had it had a big impact in machine learning and a lot of different engineering fields, because every time you try to field this big model, most of the time you want most of your parameters to be 0. You're basically saying most of the inputs are irrelevant. There are a few inputs that are relevant. And lasso basically solved that problem. And it's remarkable because Rob Tibshirani sort of introduced this model and showed the solution to this problem back in '96. And this work has, over 50,000 citations, right? So, all you have to do is to replace this q from 2 to 1. That's all you had to do, right? It's pretty remarkable. One trick, and now there are very efficient solvers, so you can scale this model to thousands of dimensions if your data has thousands of dimensions. Particularly people who work in medical imaging, whenever you're working with gene expression data, you have hundreds of millions of genes, and you try to build these sparse models. These models work remarkably well. So that's one of the few things where it made a big impact on lots and lots of engineering, medical, machine learning fields, which is pretty amazing. The above formulation also is equivalent to this particular formulation, which is you look at the sum of the squared error subject to this constraint. And so a lot of convex optimizers, it's a constraint optimization problem. In fact, it's a quadratic programming problem. So you can solve it fairly efficiently using modern tools. And these two approaches are related using Lagrange multipliers. So you can either solve it this way, or you can solve it the other way. Yeah, so lasso solution is a quadratic programming problem and can be solved fairly efficiently. And so this is just the idea of quadratic versus lasso. So you can see that, you know, sometimes these are called L1 and L2. But what's happening is that, you know, this is precisely why you can get settings where most of the parameters are close to 0. Because this is where the optimal solution is. Yeah, question? Yeah, so ultimately, you'd want Q to be 0, because that would basically say, just find me a subset of non-zero elements. The problem is that whenever your Q is 0.5 or 0, the problem is hard to solve. So there aren't optimal solutions for that problem, because it's kind of like, when Q equals 0, it's like a subset selection problem. When Q equals 1, it's more of a relaxed version, but you can solve it. Okay, now, the last point for this lecture that I'd like to make is the bias-variance decomposition. And again, we're going to come to this point later in the class when we're going to start looking at the capacity and complexities of deep neural networks. So this is a very, very important concept to keep in mind. How many of you are familiar with bias-variance decomposition? Some of you. Okay, good. So let's revisit this. So how can we control overfitting? Right? How do we find the right regularization coefficient? How do we choose it? So let's look at the expected squared loss. Right? Remember when we looked at the expected squared loss before, right? We said that it has these two terms, right? This is kind of like the variance of your targets, and this is your loss, how well your prediction fits to the correct function. And we're saying that the optimal function here is given by the conditional expectation. Okay? And this is intrinsic variability in the target value. So this is the variance of the target values. It's the minimum achievable loss. So if we model our function using some kind of a parametric function y, then there is another class of models, Bayesian models, we'll touch upon a little bit in this class. From Bayesian perspective, the uncertainty in our model is going to be expressed through posterior distribution of parameters. Right? How many of you are familiar with Bayesian models? A few. Okay. But we're going to be looking at something that's called frequentist perspective. So in statistics, there are two different standard views. One is Bayesian view, one is a frequentist view. And bias-variance decomposition really comes from the frequentist perspective. So we're going to look at that. Later on in the class, we might have a lecture on Bayesian neural nets. So I might mention that later in the class, and you'll see the Bayesian version of these models. But let's look at the bias-variance decomposition from the frequentist perspective. Let's say we have a point estimate, W star, based on a particular data set D. So given data set D, you fit the model, you get W star. Okay, you get your optimal parameters. Now, we want to interpret the uncertainty of this estimate through the following experiment. Okay, suppose we had a large number of data sets, each of size n. Okay, so instead of one ImageNet, you had 100 ImageNet data sets. Okay. Or instead of your particular one data set, MNIST data set, we had 100 different MNIST data sets. And where each data set is drawn independently from underlying distribution, right? So it's not like some data sets look weird, other data sets don't. They're really independent data sets, independent examples drawn from your data. For each data set D, we can build a prediction, right? For each data set D, we can build, let's say, a neural network function. We can build an SVM, or we can build a decision tree, or we can build, linear regression, whatever that function is, right? Remember, this prediction is going to be a function of the data set, right? Because for different data sets, these functions might differ, okay? So different data sets will give different prediction functions, obviously, right? Now, the performance of a particular learning algorithm, you're going to be assessing that by taking the average over the ensemble of these data sets. Okay? So think of it, if you have 100 different data sets, you fit 100 different functions, and your overall performance is going to be the average over all of these functions, right? Each one of them predicts, you average the predictions, that's the overall performance. So let's look at this expression, right? This is the truth, and this is your prediction, okay? Note that this quantity depends on a particular data set D, because your function, your prediction is going to be a function of that particular data set D. Now, just as we've done before, we're going to add and subtract this particular term. What is this term? Which is the expectation of all data set of your function. So it's kind of like your predictions averaged over all data sets. Okay? Now, if I do this, I add and subtract this expectation. Again, I use the trick that we've used before. I open up the parentheses. You're going to have this squared, you're going to have this squared, and you're going to have a cross term. And taking expectation over D, the last term basically disappears, right? Because if I take expectation with respect to D, and this expectation with respect to D, this expectation with respect to D, this term is going to be 0, okay? And so now, if I take an expectation, this is my prediction in a particular data set, this is the ground truth, think of it as a target, your labels or your classes. I take an expectation of all data set, I end up with two terms. The first term is known as the bias, the second term is known as the variance. Okay? What is this first term? If you look at this expression, this is basically saying if you average your predictions over all data sets, how far they are from the ground truth. Right? You can think of the bias as, let's say I pick a simple model. I pick like a linear regression model, just a line. I fit the line to my data. This term might be pretty high, right? Because you have a simple model, right? The second term is basically saying, the second term has nothing to do with predictions. The second term is basically saying how much different each individual prediction compared to the average of all data sets, right? And this is known as the variance, which basically has the following property. Let's say your boss gives you the data. You fit the model. You say, it looks great. Your boss gives you slightly different data. You come up with a completely different model, right? Then you get slightly more different data. You get a completely different model. That would mean that your variance is very high, right? That's also bad. So you have these two terms. The first term is really saying, you know, how far on average you are from the ground truth. The second term is saying how much individual functions are tuned to your data set, right? Both of them are bad. So try to reduce both. So let's look at it in a little bit more so the expected loss has bias. And this is, again, this is average predictions of all data sets, how they differ from the optimal regression function, right? This is essentially telling that you don't want to fit simple models. You want to fit, you know, complex models so that the difference between what you're fitting and the ground truth is small. The second term is basically saying solution to individual data sets vary around their averages. How sensitive is the function to a particular choice of a data set, right? Obviously, you don't want your functions to be sensitive to a particular choice of the data set, right? And then there is intrinsic noise. So now you have this trade-off between bias and the variance. Basically, if you have very flexible models, high complexity models, think of building, you know, a model with lots of basis functions, or think about building a very complicated neural network function. You're going to have low bias, right? You're going to have low bias because the model is complex enough. It can model your true function, but you're going to have high variance. Right? Because you get to see, you know, a small data set, or you get to see, you don't get to see the whole, you know, infinite data. You get to see some fixed data set. So you're going to have high variance. But at the same time, if you have relatively rigid models, right? You have simple models, low complexity, you're going to have high bias because maybe the ground truth is going to be far away from the truth, but you're going to have low variance, right? Your prediction is not going to vary that much if the data set changed a little bit. Think of, you know, a model that always predicts 0. I give you a different data set, I'm still going to be presenting 0. The variance is 0, right? And that's the simplest possible model you can build, right? And so the model with the optimal prediction capabilities, you have to balance these two terms, bias and variance. So later on, when we're going to talk about deep neural nets, we're going to come back to this particular point because there is a thinking of, okay, how do we control bias versus variance? Given a particular data set, we don't want our model to be too complicated because we're going to overfit. So we're going to have high variance. At the same time, we don't want our models to be too simple because they're going to have high bias. So there was a question? Yeah, okay. Yes. So this particular thing is, we've looked at particular just squared loss, right? Generally speaking, if you look at other losses, it's not quite as clear, but in general, this decomposition does hold, right? For different loss functions, like, if you look at classification, if you look at cross entropy, you look at other, L1 loss functions, generally you can derive something similar to that. So this is more common of a decomposition bias, which intuitively should make sense, right? Intuitively, it's saying, ultimately, I want to build simpler models. The question is how much bias you have, versus if I want to build complex models, how much variance I have, because I'm going to be tuning to a specific data set. So here's just an example to illustrate this point. Suppose that, remember we looked at the sign data set, and let's say we generate 100 more data set, each containing 25 data points, drawn independently from the same underlying distribution, right? From the same sign function, same noise, right? So if I have fairly small regularization term, right? And I'm fitting, in this case, I guess I'm fitting a 14-degree polynomial. No, in this case, I think it's 9-degree polynomial. Then if I don't regularize my model, I'm going to have high variance. Because you can see for different data sets, these functions are different. But if I average those functions over all of these data sets, I have low bias, right? Which basically means that if I had more data, I would have perfect model, right? But if I only get to see a data set with 25 data points, this might not be good because I can give you a function that looks like this, too wiggly. Here's an example where we increase the regularization. So it's kind of like, there is some variance, but smaller, right? The variance is smaller here, but you have a stronger bias. And here's an example of, I really regularize my model. And so it has smaller variance, like different data sets, your underlying functions don't vary that much, but I have high bias, right? It's not quite the right model. So the optimal model kind of like lies somewhere in between these two terms. Of course, in practice, you can't compute exactly the bias and the variance unless you're working in very specific scenarios. So that's something, non-trivial to figure out what is the right trade-off. Yes. Yes, that's right. Each wiggly line in the top row corresponds to fitting a different data set, right? And obviously, in practice, you don't have access to 100 different data sets. Because if you have 100 different data sets, you just put them into one big data set, right? And you still end up with the same problem. And so here, it's a Bias-Variance Trade-off. This is just a simple example for the sign data set, toy data set. But you can see that as you increase the regularization parameters, you're forcing your model to be less and less complex. Your bias increases, but your variance decreases. And ultimately, there is some optimal choice over here. And this is the test there. It decreases and then increases. So you kind of like want to be sitting somewhere here. How do you beat Bias-Variance Trade-off? You can do a couple of things. And this is commonly done in practice, is you can reduce the variance by averaging over many models trained on different data sets, right? So this is something that you have big data set, you partition into different subsets of the data, you train different models, you average them. But in practice, you only have a single data set, right? And if you had many independent training sets, you'd better be combining them into one large training set. With more data, you have less variance. this is generally the case. With more data, you will have less variance, obviously, right? So that comes back again to the point that in machine learning, really, people are trying to figure out how I can get more data. So I can fit complicated functions, but with more data, I'm obviously going to have less variance. But at the same time, you can also do the following. Given a standard training set D of size n, let's say you have n training examples, you can generate new training sets by sampling examples from D uniformly with replacement. Right? So what you could do, and that's what sometimes known as a bagging approach, which is have your data set, just sample k data sets by sampling examples with replacement. So some examples are going to be repeated, some examples are not going to be repeated. Or some examples will not appear in your data set. So you're basically trying to come up with some version of data sets. Oh, of course, they're going to be correlated, right? Because examples are going to be repeating similar examples. But at least it can help you. And this is called bagging. It works quite well in practice. And so this is something that people are doing. There is also a technique called bootstrapping, right, which is sort of related to bagging, which is again based on this idea that you can draw multiple data sets with replacement, fit different models on these different data sets, and try to see, try to estimate the variance. It can tell you something about function you're fitting. Yes.
This bias-variance trade-off applied to deep learning model is very complicated. Often overfit to the training.
We'll come to that. We'll come to looking at the bias-variance decomposition for deep networks later. But they fall into the same kind of paradigm. Yeah. And so even in deep learning, people sometimes use bagging, where you can train on different subsets, you can average the predictions, or you can at least try to estimate what's the variance. And so there's also a related thing called bootstrapping. I mean, if you haven't heard about bootstrapping, you should look. And I should also point out that bootstrapping was also developed by Rob Tibshirani. And if you look at the number of citations, there are like 60,000 citations. So it's incredible that you have two techniques, very simple techniques, being so influential. But nonetheless, yes. Yeah, it's fairly similar to that. Yeah. Okay, so and then there is also another technique, which is the Bayesian framework, which is kind of a little bit more computationally intensive. And in the deep learning community, if you look, there are a few workshops called dedicated to Bayesian deep learning. And the idea here is that you're going to be combining the predictions of many different models using the posterior probability of each parameter vector as a combination weight. So basically saying, what's the posterior probability of my parameters in the model? And you can try to, integrate out, all over the parameters in your model. We'll probably look at some of these techniques later. They're much more computationally intensive, but they work fairly well as well. Okay, so let me now jump into what's supposed to be the second lecture, but will probably be split into multiple lectures because we don't have a lot of time, so we're going to cover it in the next class. But I wanted to spend one more lecture just looking at the basic probability distributions. Because when we're going to start looking at classification, regression, when we're going to start looking at variational autoencoders and Boltzmann machines, you have to be familiar with concepts like basic probability distributions. You have to be familiar with concepts of exponential family models. How many of you have heard about exponential family models? Some. Okay, good. So this is something that we'll have to cover because, and again, I encourage you to look on the web. There's a reading material. Look at the deep learning book. Look at the Chris Bishop's book, because those are the concepts that you should be familiar with. And as we go through the rest of the class, I'll refer to these concepts, and the expectation is that I'm not going to be diving into details about these distributions, or what's the meaning of exponential family models, or what is the natural parameter, and so forth. Okay. Okay. Very quickly, just the next, I guess we have 10 more minutes. By the way, before I get there, are there any questions? It's either very simple or very complex. right? Yeah. Okay, good. Let's make an assumption that it's trivial. So we're going to look at the Bernoulli distribution. It's one of the most simplest distributions. You have a single binary random variable. For example, I can describe an outcome of a flipping coin. So if it's heads, if it's ones, tails, if it's 0, the probability that x being 1 is going to be denoted by parameter mu. So we can say probability that x takes value 1 is given by mu. And that's the parameter that we're going to be estimating. And this probability distribution is as a Bernoulli distribution, right? It really is the distribution. You take mu, power of x, 1 minus mu to the power of 1 minus x, right? So if x is 1, the probability that x taking value of 1 is going to be given by mu. The probability that x takes value 0 is going to be given by 1 minus mu, right? Pretty simple. Expected value is the mu, variance is mu1 minus mu. Later in the class, we're going to look at the class of models called restricted Boltzmann machines, or Boltzmann machines. And this is an ensemble of these Bernoulli variables, right? Anytime we're going to be modeling binary data, we're going to be using Bernoulli distributions. So you kind of like should be familiar with Bernoulli distributions pretty, it should kind of like feel right when you look at Bernoulli distributions. Parameter estimation given a data set D, again, you can construct the likelihood function. Same thing. The joint probability distribution of the data set D is just given by the product of individual terms. You maximize the log, so you take the log. The product turns into the sum. That's the sum, a little bit of algebra. One key observation to make is that this likelihood function, log likelihood function, depends on an observation, xn, only through the sum. Okay? And sometimes this is known as a sufficient statistics, right? What that means is that I don't actually have to tell you the entire data set. All I have to tell you is the sum of the outcome of the flipping coins. Like if I'm flipping coins 1,000 times, all I need to tell you is the number of heads. It's 526, that's it. Because that's the only thing that I need in order to figure out what are the parameters that maximize my log likelihood function. Right? All right. I think my PowerPoint died. Let's see. Yeah. Let's just see. I don't want to report it. I've been reporting it for so long. I think it just goes to. I think it just goes to the junk mail. Let's see. Sorry about that. Let me just. There it is. Let's hope it's not going to die on me again. Okay. Okay, so now if I set the way that you always do maximum likelihood, and again, when we're going to look at more complex models like Boltzmann machines, variational encoders, and such, generally we're going to be writing down the likelihood function or some form of the log likelihood function. And the way you can think about performing optimization is you take derivative of the log likelihood function with respect to parameters, right? And either solving it exactly or doing some kind of gradient descent. Okay? So this is an example where we can just take the derivative of the log likelihood function with respect to the parameters, we set it to 0, and we get the maximum likelihood solution. And the maximum likelihood solution is pretty trivial, right? It's like the number of heads out of total coin flips, right? So if I want to estimate what's the probability of seeing a head in a coin flip setting, I just flip it 1,000 times and I look at the fraction of heads that I see. That's my maximum likelihood estimation, right? Pretty trivial and should be intuitive. Now, another class of distributions is the binomial class of distributions. And the idea here is that it's the probability of observing m heads given n coin flips. So this is kind of an extension of Bernoulli distribution by basically saying, what's the probability that I'm going to be observing 300 heads at 1,000 coin flips, right? And this is, given by n choose m, m to the power of mu to the power of m, 1 minus mu, n minus m, right? So it's just a simple extension of Bernoulli distribution. And again, the mean and the variance can be simply computed as these expressions. I'm not expecting you to memorize these expressions, but you should kind of have an intuitive idea what the binomial distribution is. Okay? And this is just an example of a binomial distribution when m equals 0.25, right? So it's basically saying what's the probability of observing 8 heads if the probability of seeing a head is 0.25. So you can see it's actually pretty small. Right? And that's the binomial. Bernoulli distribution just really gives you the outcome for one thing. What's the probability of observing a coin fling being head? And this is more if you draw multiple trials. Beta distribution is another class of distributions where you basically define a distribution over the mu, which is in a 0, 1. So effectively can be used as a prior of a parameter mu in the Bernoulli distribution, right? So it defines that way, where the gamma function is defined that way. I'm putting this slide for your references. Again, I'm not expecting you to memorize these things because you can always look them up on Wikipedia, but it's important to visualize what these distributions look like, right? It's a distribution over an interval 0 to 1. Right? So that's why sometimes it can be used as a prior over Bernoulli models. If you look at the Bayesian, if you're interested in Bayesian models, these distributions are heavily used. And this is just an example when A and B, these are two parameters of the distribution, are 0.1, 0.1, you kind of like assign more probability mass between 0 and 1, right? Or if it's 2 and 3, you assign some more probability mass in this space, right? So you can model fairly complicated distributions on the interval 0 to 1, okay? And that's a beta distribution. It's a useful distribution to know about. Let me just get into the multinomial variables and then we'll stop. This is the one that we're going to be heavily using across the rest of the class, particularly when we're going to start looking at classification problems. So this is something to be familiar with. Suppose that you have a random variable that can take on one of k possible mutually exclusive states. Think of doing classification. I have 10 different classes, and I can only take one value. Like, in the image, I can have 10 different classes, but what I observe is only a single instance of that class, of that particular input. And we're going to be using one of k encoding scheme. Or if you roll a die, the state of the die gives you one particular state. These are mutually exclusive states, right? So in the case of images, this is commonly used for image classification problem. If I show you an image, this is an image of a cat. So out of all possible classes, I say, it's 1 for the cat, 0 everywhere else, right? It's not like I show you an image, I can say, yeah, 0.5 it's a cat, 0.5 it's a dog, right? That's, your model can make that prediction, but when you are setting up the problem, you're making assumptions that classes are mutually exclusive. So if the random variable, for example, can take on k states for a particular observation, we're going to be using one of k encoding scheme, right? So one of k encoding scheme is going to be represented by this expression, right? So if this particular x belongs to state 3, then it's 0 for all the states and 1 for the states that you're observing, right? And if we denote the probability of this kth value being taking value 1 by the parameter mu sub k, then the distribution is going to be defined this way, which is just the extension of the binomial of a Bernoulli case, right? All of these mu sub k's should be greater than 0, and they have to sum up to 1. Let me actually stop here, and then we'll continue on Wednesday. So please do have a look at the reading material. There's a whole bunch of things you should be reading.
I like the lecture very much. And yeah, I think especially the bias.